Alrighty, so this video covers one of the most foundational and fundamental techniques for solving antiderivatives, for helping us solve integrals that exists. It is our first foray into trying to solve integrals that we don't just have a simple antiderivative for. And so maybe to kind of give you an idea, right, if I were to hand you cosine of x, right, we might say, okay, I know that the antiderivative of this thing is sine of x, no problem. But what if I were to give you something that looks like sine of x over cosine of x, right? Something like this, which you may famously recognize is tangent of x. But there, we know the derivative of tangent of x, right? The derivative is secant squared. But what's the antiderivative, right? What function has a derivative that is equal to tangent of x if we were to go backwards? And so this technique is useful in very specific situations, and it's kind of a good time to kind of bring up that in calculus, or in especially in integral calculus, right, one of our big focuses is to solve integrals of this form. And the thing is that sometimes it's very easy depending on what f of x is, right? If this is just 1 over x, then we know, for instance, that the answer is the natural log of the absolute value of x plus c, right? But the problem is that there is a whole world of harder functions, right? Harder, more complicated functions. And truth be told, right, most of them we can't even do the antiderivative of. It turns out. So like when taking a derivative, there's lots of functions we can take the derivative of, and our rules are pretty comprehensive. But when it comes to solving antiderivatives, it's actually the case that there are more antiderivatives that we can't solve than ones that we can. But regardless of that phenomenon, we are going to start building a catalog or a toolbox that's going to help us solve as many of these integrals as we can in this class. And so you'll notice that, the class is kind of broken down in such a way where you're going to learn a whole bunch of different techniques. And in each section, I'll try and provide a caveat, that this tool, in this case, this tool that we're going to learn about called U-substitution, only works if we select, or we're given very particular type of functions to take the antiderivative of. If we're not, or it doesn't fit the form or something like that, we cry ourselves to sleep and we're going to have to give up. So take everything that you learn about U-substitution or the future techniques with a grain of salt, which is that, this all only works in very specific scenarios, but thankfully those scenarios are going to come up quite a bit, so hopefully it won't seem so out of left field. But let's get down to the idea of this video. Okay, so in calculus, we learn about a whole bunch of derivative rules. We learn about the power rule, right? That's the first one. That's like if we have x squared and we bring down the exponent and all that good stuff. But we already learned how to undo the power rule. We can basically just do a simple antiderivative. We call them just the elementary antiderivatives. You just undo the power rule, no problem. But there's a whole bunch of other derivative rules, right? There's the product rule, there's the quotient rule, there's the chain rule, right? And I'd say that, the most important one of those, the one derivative rule that shows up in every single derivative is going to be the chain rule. And so our goal, the goal of this video is to learn a technique that helps us identify that the chain rule has happened and lets us figure out how to undo it. So maybe I'll write that down. So U-substitution, or what we abbreviate as a U-sub, a U-sub is going to help us identify that the chain rule has taken place. So it's going to help us identify that the chain rule has taken place, and it's going to inform us how we go about handling that particular antiderivative. So a U-substitution is going to help us identify that the chain rule has taken place and figure out a way to make our integral easier to solve. So a way to make our integral easier to solve. Okay, and so what do I mean by this? So what I mean is for instance, so if I were to give you a particular function, I were to say like y is equal to, like let's say e to the 3x, we know with enough practice from Calc 1 that the derivative of this thing would be, it's e to the 3x, but then there's this multiplied by the derivative of what's in the exponent, so multiplied by 3, which I'll just put there in the front. Right? And we'll do a couple of these examples. So another example that involves a chain rule would be if we had y is equal to the natural log of, let's do like x cubed plus x, right? Then the derivative is equal to, okay, so the derivative of the natural log of something is 1 over that something, so 1 over x cubed plus x. But then we have to multiply by the derivative of what's on the inside here, courtesy of the chain rule. So we're going to multiply by 3x squared plus 1 to get our final answer. And maybe kind of just one more to drive the point home. Maybe if I have y is equal to sine of e to the x, then the derivative of this thing is going to be cosine of e to the x. But then we have to multiply by the derivative of the thing on the inside, which for us is the derivative of e to the x, and that's just e to the x. And the reason why I'm bringing up these examples is that if I had started you in a Calc 2 course and I said, look, I want you to do the integral of 3e to the 3x dx, right? Or maybe I wanted you to do the integral of 3x squared plus 1 over x cubed plus x dx. And lastly, right, I wanted you to do the integral of e to the x times cosine of e to the x dx. If I were to just give you these at this point in the class, I wouldn't really expect that we would know how to do them. Maybe we could figure out a way to navigate this first one, but the rest of them, we can't just do an antiderivative like we've been doing. So for instance, this one, just like with the derivative, right? When we took the derivative of a quotient or of a rational function, we didn't just say the derivative is just, the derivative of the top over the derivative of the bottom or something like that. There's more to it. And so, you can't just take the antiderivative of pieces of this. We have a big complicated function. There's a lot more going on to it. Same thing here. We have the product now with two functions. We have the product of e to the x with cosine of e to the x. We can't just say, the answer is the antiderivative of this times the antiderivative of this. Like, what even is the antiderivative of cosine e to the x? Right? We don't know. But, the reason why I'm putting these kind of side by side is that we're kind of hoping to basically try to identify that if we have some sort of function, say like e to the 3x, and we can identify, or we have a guess, that the chain rule has taken place in some way, shape, or form, right? So here we have 1 over x cubed plus x, and we kind of astutely notice that the derivative of that is kind of sitting up here in this problem. And same thing in the bottom one, which is, that we have an e to the x here, but the derivative of e to the x is also e to the x, and that also happens to be sitting in this problem. This is kind of like we're trying to build some intuition for how we can identify that we're going to need to use this tool called U-substitution. And the idea is that we're trying to identify that the chain rule has taken place, and that's going to inform us, okay, it's probably time to try to do a U-substitution. Okay, so before we do that, I'm going to give you an analogy to something that we have done before that you may have forgotten, but it's way back in maybe like Algebra 1 or Pre-Calc 1 or something like that. Do you all remember when we used to have something like x to the 4th plus 2x squared plus 1 is equal to 0? And back in the day, we used to try and solve something like this, and we're like, oh man, this is impossible, right? But the technique that we had to solve something like this was we said, well, wait a second. What if we make a good observation, right? We had to make an observation. This thing kind of looks like a quadratic. It's not perfectly a quadratic, but it kind of looks like one. And if we had that intuition, right, we recognize that maybe something was going on here, we might say, well, let's let u equal x squared. And if we do that, right, if we made this choice, then we could say, well, then, right, then u squared would be equal to what? Well, if I square this, x squared squared becomes an x to the fourth. And so then we can write, so our example, or so our problem, right, it's now not x to the fourth, it's going to be u squared plus 2u plus 1 is equal to 0. And this thing looks exactly like a quadratic that we know and love. And we could solve this doing a whole bunch we could just factor this, right? This thing would just factor into u plus 1, and u plus 1 is equal to 0, right? We could solve this one, and then we go back and try and solve that one. We could use the quadratic formula. There's a whole bunch of things that we could do to try and solve it from here. But the big thing is that two things needed to happen. The first thing that needed to happen is that our problem that we had to have been given has to magically, allow this to happen, right? It has to be in a form that if I were to choose to make this substitution here, that it's all going to perfectly magically work out. So for instance, if I had just had something like this, then my technique over here doesn't work anymore because there is no x squared to substitute in, right? If I make this same substitution, I wouldn't have a u here, I'd have a square root of u. And now this isn't really any better than the first thing that I had to solve in the first place. So that's like one big thing to notice. But the other idea that's more important to notice is that what we're doing is that we're starting off the problem in what I'm going to call xland. I'm going to say here is xland where we started our problem. We had like x to the fourth plus 2x squared plus 1 is equal to 0. And the problem is that solving it over here is hard. It's hard to solve if we hang out in xland. And so what we do is we decide to go to a new land. Let's call it U-land. Right? We head on over to this new world over here, and we take a boat. And that boat that we take is one that we create. So we build our boat. We say we're going to get over there by letting u equal to x squared. This is kind of like our conduit. This takes us from xland to u-land. And if we do this thing, then, using this, what we call a transformation, which should kind of feel like an appropriate name for this, right? We're creating a transformation, something that is going to transform this equation into something in u-land. And so we already saw what it becomes, that in u-land it becomes u squared plus 2u plus 1 is equal to 0. And now this is much easier to solve, right? So it's easier to solve now that we're in u-land. And so we could do that, right? We right? We get u plus 1 squared is equal to 0. We therefore get that, u plus 1 has to equal 0. That's going to give us that u is equal to -1. Great. We have now solved the problem. Hooray. Or at the very least, we've solved kind of a version of it, right? We have the original. We kind of transformed it to look a little bit different. It's still the same problem. It's just dressed up a little bit different. And we solved it. And so what's the last thing that we need to do? Well, we didn't start off in u-land, right? We started off in xland, and the people that we're trying to give this answer to live in xland. So we need to go backwards, back over here. And how are we going to do it? We're going to use the same transformation that we had before, which is going to say, oh, wait, so the solution to this original problem, the solution to this thing is going to be, well, if u is equal to x squared, then the solution is going to be x squared is equal to -1. And then we could solve this for x as we go. And if we were dealing with imaginary numbers, this would be plus or minus I. But if we weren't dealing with imaginary numbers, we would say maybe then that there's, no solution, right? But the whole point is that we went from working with something that looked really hard, scary, and kind of difficult. We made an educated guess as to what we wanted to let this u be, right? Based on some previous experience we have working with quadratics. That turned our equation into something else in U-land. And then once we solved the problem in U-land, right, once we did the easy math, we just kind of took the train back and we said, okay, I can get my final answer in x's over here, right, whatever it is that we're trying to do. And so in making this substitution, our life gets a lot easier. And so how does this relate to what we're doing? So what you're going to see in the next video is me kind of working with this concept, which is that our goal is going to be to take integrals like this, and we're going to use our collective experience in recognizing that the chain rule has taken place to make a very particular substitution to go to what I'm going to call U-land and create an integral that is easier to solve than the one that we've been given. Right, we're going to go over to U-land, and then we're going to come back when we're all done to get our answer back in terms of x's. So this video is primarily just to serve as an intuition for what the heck's going on. What this technique is all about, and a lot of the intuition behind what it is that we're going to be doing. And then once you have this intuition and you feel like you have a good footing under you, head on over to the next video where we're going to start trying to work through some examples.